the black hole revolution. There is something fundamentally captivating about the universe's most violent phenomena. And I'm not talking about supernovas or gamma-ray bursts, phenomena that we've studied and understood for decades. I'm talking about something far more mysterious, far more bizarre, and frankly, far more mind-bending than anything we thought possible just a few years ago. I'm talking about black holes, and specifically about black holes doing something that they absolutely were not supposed to do according to everything we thought we understood about physics. Before we can even begin to appreciate what's happening right now at the bleeding edge of astrophysics, before we can understand why this discovery is reverberating through the scientific community like nothing since perhaps Einstein's original formulation of general relativity itself, we need to step back and understand the foundations. We need to understand how we got here. We need to understand what physicists have believed about black holes for the better part of a century, and why those beliefs seem so ironclad, so supported by mathematics and observation, that the idea of black holes violating those expectations seemed completely absurd. We need context. We need history. We need to understand the intellectual landscape that makes this discovery so revolutionary. Your understanding of the universe, my understanding, every physicist's understanding, is built on thousands of years of accumulated observations, experiments, theories, refinements, and occasionally wholesale revolutions in thinking. From ancient philosophers in Greece asking fundamental questions about the nature of matter and motion, to medieval scholars in Baghdad trying to reconcile observation with theological doctrine, to the scientific revolution of the 16th and 17th centuries where mathematics became the language through which we could describe nature with unprecedented precision and accuracy. From the Industrial Revolution that transformed how humanity interacted with the physical world, to the electrical revolution of the 19th century that revealed entirely new forces and phenomena, to the quantum revolution of the early 20th century that showed us that reality operated according to principles that contradicted our everyday intuitions. Each generation of scientists inherited the framework from the previous generation and either refined it incrementally or, occasionally, revolutionized it entirely. And in our modern era, particularly in the 20th century, we've experienced revolutions in understanding that would have seemed literally impossible to the greatest scientific minds of the 19th century. We learned that light was both a wave and a particle, depending on how you measured it. We learned that atoms weren't indivisible but were composed of even smaller subatomic particles. We learned that particles could be entangled across vast distances, affecting each other instantaneously in ways that seem to violate the cosmic speed limit of light, yet somehow don't. We learned that time was not absolute, that observers moving at different speeds would disagree about whether two events happened simultaneously. We learned that space wasn't empty, that the vacuum of spacetime was seething with quantum activity. We learned that the universe could expand infinitely in all directions yet still be finite in volume. We learned that the universe had a beginning, a moment called the Big Bang when everything we observe today was compressed into a point of infinite density. These weren't just corrections to previous understanding, the way we might correct a small error in a calculation. They were wholesale reimagining of what reality actually is at the most fundamental level. They shattered intuitions that had seemed self-evident. They forced us to think in ways that contradicted everyday experience. They opened up entirely new domains of understanding and possibility. What we're experiencing right now in 2026 with these black hole explosions that scientists have recently confirmed is another one of those revolutions. Another moment where observation forces theory to bow before the facts of how the universe actually works, regardless of how unexpected those facts might be. And I'm emphasizing this because I want you to understand, deeply and viscerally, just how stunning this discovery is. This isn't a minor refinement to our understanding of black holes. This isn't a footnote in the margins of textbooks, something that specialists will debate at conferences, while the broader understanding of the public and of the field remains largely unchanged. This is a reshaping of fundamental assumptions about how the universe operates at the most basic level. This discovery will force physicists to rethink not just black holes, but the nature of information, the structure of spacetime, the relationship between quantum mechanics and gravity, and ultimately what the universe fundamentally is. In 1905, a young patent clerk in Bern, Switzerland named Albert Einstein published 4 papers that would fundamentally reshape how humanity understood the universe. One of those papers introduced the special theory of relativity, overturning centuries of assumptions about the nature of space and time. It showed that there was no absolute reference frame, that simultaneity was relative, that time could dilate, that space could contract. These weren't minor corrections. They were fundamental reconceptualizations of what space and time actually are. And yet, they were soon validated by countless experiments and observations. But Einstein didn't stop there. He spent the next decade wrestling with gravity, trying to reconcile his insights about relativity with Newton's theory of gravitation. And in 1915, he published his general theory of relativity, which completely reimagined what gravity actually is. Before Einstein, gravity was understood through the framework that Isaac Newton had provided centuries earlier. Newton's theory of universal gravitation was elegant and successful. It explained why objects fell to the ground when you released them. It explained the orbits of planets around the sun with stunning precision. It explained the motion of the moon around the Earth. It explained the motion of comets and the behavior of tides. It was extraordinarily successful at making predictions, so successful that it had become difficult to even imagine an alternative framework. Newton's gravity was the standard, the framework within which all physics was understood. Newton's theory said that gravity was a force, that objects with mass pulled on each other across the empty space between them through some kind of gravitational action at a distance. The strength of this pull depended on how massive the objects were and inversely on how far apart they were. The force was instantaneous. If you moved one massive object, the gravitational effect on distant objects would be felt immediately. This framework worked beautifully for nearly 300 years. But there was a problem. Maxwell's theory of electromagnetism, developed in the late 19th century, suggested that nothing could travel faster than light. Light was the ultimate speed limit in the universe. If gravity exerted itself instantaneously across any distance, as Newton's theory suggested, then gravity would violate this cosmic speed limit. And beyond this theoretical concern, there were small but measurable discrepancies between Newton's predictions and observation. Tiny deviations in the orbits of planets that couldn't quite be explained by the presence of unseen planets or other minor factors. Einstein's general theory of relativity solved these problems with a radical reconceptualization. Gravity isn't a force pulling on objects through empty space, Einstein said. Instead, mass and energy curve the spacetime in which they exist. Spacetime is like the fabric of reality itself, the stage upon which all cosmic phenomena play out. And massive objects create indentations, wrinkles, valleys in this fabric. Objects then follow the straightest possible paths through this curved landscape. From the perspective of an object, it's moving in a straight line, following an inertial path. But because the space itself is curved, the object traces out a path that we perceive as a curve, like the orbit of a planet or the trajectory of a falling object. This was revolutionary. This wasn't just a refinement of Newton's theory, adjusting some parameters or adding correction terms. This was a completely different way of thinking about gravity. Gravity wasn't a force. It was geometry. It was the shape of spacetime itself. The equation that Einstein derived, the field equation, related the curvature of spacetime to the distribution of mass and energy within it. Matter tells spacetime how to curve, and spacetime tells matter how to move. And crucially, changes in the curvature of spacetime didn't propagate instantaneously. Changes in the curvature of spacetime propagated at the speed of light. If you moved a massive object, the change in how spacetime was curved would ripple outward at light speed, no faster. This was consistent with Maxwell's electromagnetic theory. Einstein's theory unified gravity with special relativity, bringing gravity into the framework of modern physics. The predictions of Einstein's theory were strange and counterintuitive. Light would be bent by massive objects. Time would pass at different rates in strong gravitational fields. Objects moving at different speeds would disagree about time intervals and distances. A clock running at the bottom of a well would tick slower than a clock at the top. Observers in accelerating reference frames would feel artificial gravity. Yet observation after observation confirmed Einstein's predictions. Now here's where things get really interesting, and this is crucial for understanding what happens next. Einstein's theory of general relativity is built on equations. Beautiful, elegant equations that relate the curvature of spacetime to the distribution of mass and energy. These equations describe how matter and energy warp the fabric of spacetime, and how objects respond to that warping by accelerating and moving along the curved landscape. But equations have solutions, mathematical answers. In mathematics, when you have an equation, you can solve it, find the values that satisfy it. Sometimes there's only one solution. Sometimes there are multiple solutions. Sometimes the solutions seem physically unreasonable or impossible, but they're mathematically valid. And in 1916, just a year after Einstein published his field equations, a German physicist named Karl Schwarzschild found one of these solutions. Schwarzschild was working in the German army as an observer in World War I when he found the solution in the trenches, working on the theory of general relativity amidst the horrors of warfare. Schwarzschild found a solution that described the spacetime around a perfect sphere of mass, an idealized situation where all the mass was concentrated at a point and surrounded by complete vacuum. It was a mathematically exact solution, not an approximation. And this solution had a deeply strange feature. The Schwarzschild solution described a region of spacetime, a sphere surrounding the mass, from within which nothing, not even light, could escape. There was a boundary which we now call the event horizon, and once you crossed that boundary, once you fell inside, there was no way out. The geometry of spacetime itself made it impossible. The curvature was so extreme that every possible path, and in relativity, what objects can and can't do is determined by the geometry of spacetime. Every possible path led deeper into the singularity at the center, where the curvature became infinite and all the normal rules of physics broke down. This was the mathematical description of what we now call a black hole. The name came later. The term black hole wasn't coined until the 1960s. Initially, these objects were called frozen stars or collapsed stars or other terms. But the idea was the same: a region of spacetime so warped that it created a trap, a one-way valve in the fabric of the universe. And here's the crucial thing. Einstein himself didn't believe they actually existed. He thought there must be some physical process that would prevent matter from being compressed to such an extreme density. He thought that the Schwarzschild solution was a mathematical curiosity, an artifact of the equations, but nothing you'd actually find out in the cosmos. Nature, he believed, had a way of preventing the formation of such bizarre objects. And Einstein, having already revolutionized physics twice, had tremendous authority. If Einstein said black holes probably didn't exist, most physicists were inclined to believe him. But as decades passed and astronomical observations accumulated, the evidence became harder and harder to ignore. Astronomers were discovering objects in the universe that didn't fit neatly into existing categories. There were objects that were far too dense to be normal stars. There were regions at the centers of galaxies that exerted enormous gravitational pull on nearby objects yet appeared to have no visible mass. Stars in the center of our own galaxy, the Milky Way, were orbiting around what appeared to be a completely invisible object with a mass 4 million times that of the Sun. The only object whose properties were consistent with what was being observed was the black hole. By the 1960s, physicists like Roy Kerr had extended Schwarzschild's solution to describe rotating black holes that were spinning. The Kerr solution was even more complex, but it was also more realistic because most objects in the universe spin. And it turned out that rotating black holes had different properties than non-rotating ones. They had an additional boundary, an inner event horizon, and an interesting region outside the event horizon called the ergosphere where the spacetime itself was dragged around by the spinning black hole. By the 1970s, astronomers had identified objects that seemed almost certainly to be black holes. There was a binary star system called Cygnus X1 where a normal star was orbiting around an invisible companion object. The invisible object was pulling material off the normal star, creating an accretion disk, a spiral of material falling inward. This material was being heated to millions of degrees and was radiating tremendous amounts of X-rays. The properties of this system, the mass of the invisible object, its density, its radiation properties, all pointed to a black hole. And then, in 1974, Stephen Hawking made a discovery that would fundamentally change how physicists thought about black holes. Hawking realized that if you applied quantum mechanics to the region near the event horizon of a black hole, something unexpected happened. The black hole wasn't completely black. It wasn't an inert object that just sat there, pulling things in and keeping them trapped forever. Instead, the black hole was warm. It had a temperature, could emit radiation. It would slowly evaporate. This was astonishing. This went against decades of thinking that treated black holes as permanent features of the universe. Hawking showed that black holes were thermodynamic objects with properties similar to hot bodies. They had entropy, a measure of disorder or information content. They had a temperature that depended on their mass. Smaller black holes were hotter, larger black holes were colder. They radiated energy in the form of what we now call Hawking radiation. And crucially, they had a finite lifespan. Given enough time, a black hole would radiate away all its mass and disappear completely. The mechanism by which this happened was bizarre and counterintuitive. Near the event horizon, quantum mechanics says that the vacuum isn't empty. It's seething with activity. Virtual particles are constantly popping into existence and immediately annihilating each other. This quantum foam is always happening everywhere in every part of spacetime, a consequence of the uncertainty principle. But near the event horizon, the gravitational field is so strong that it can sometimes separate a virtual particle-antiparticle pair before they can annihilate. One particle falls into the black hole while the other escapes. From the perspective of an observer outside the black hole, it looks like the black hole is emitting radiation. And that radiation carries away energy that had to come from somewhere. It comes from the black hole's mass. So the black hole slowly evaporates, losing mass gradually over time. This was the solution to a problem that had bothered physicists for decades. If black holes were completely black, if they trapped everything inside them, then information would be lost from the universe. This would violate a fundamental principle of quantum mechanics. That information cannot be destroyed. According to the foundations of quantum mechanics, physical systems evolve according to unitary evolution, transformations that preserve information. But if black holes could destroy information, trapping it inside their event horizons and keeping it there forever, then quantum mechanics would be violated. However, and this is crucial, Hawking's original calculations suggested that the radiation was simply thermal. It was like the radiation emitted by any hot object. It had no particular structure. It didn't seem to encode information about what had fallen into the black hole. And so physicists were left with a paradox. If information couldn't be destroyed, but black holes appeared to destroy it by trapping matter inside and evaporating without releasing that information, then something was wrong with either quantum mechanics or general relativity or both. This became known as the black hole information paradox, and it has been one of the deepest, most troubling problems in theoretical physics for the past 50 years. How could the universe respect the fundamental conservation of information yet have these objects that seem to violate it? It was a profound puzzle, a crack in the foundation of modern physics. Through the latter part of the 20th century and into the 21st century, astronomers developed increasingly sophisticated techniques for observing black holes. They couldn't see black holes directly. Black holes are, by definition, black. But you can observe their effects on nearby matter, the way they warp spacetime and affect the objects around them. When material falls toward a black hole, it doesn't plunge in immediately. Instead, it spirals inward due to the fact that it has some angular momentum. As it spirals, it's accelerated to tremendous speeds. Friction between different layers of the infalling material heats it to millions and billions of degrees. This hot material emits radiation across the electromagnetic spectrum: visible light, ultraviolet light, X-rays, gamma rays. The radiation across these different wavelengths carries different information. By observing this radiation, astronomers could infer the presence of a black hole and study its properties. By the early 21st century, astronomers had identified dozens of black holes and studied them with increasing precision. Some were isolated objects. Some were in binary systems with companion stars, where they were pulling material off their companions. Some were massive objects at the centers of galaxies. And scientists had developed good models for how matter accreted onto black holes, how that material was heated and accelerated, how it emitted radiation. These models were successful. They could explain most of what was observed. They could account for the overall power output, the spectrum of radiation, the timing of variations. But there were anomalies. There were observations that didn't quite fit the standard models. Black holes that seemed to be putting out more energy than their accretion rate should allow. Black holes that showed sudden violent outbursts that seemed inconsistent with gradual, smooth accretion. Radiation patterns that had subtle structure and patterns that didn't match expectations. The correlations between different wavelengths and different times that seemed too structured to be random. For decades, these anomalies were treated as curiosities, interesting but not revolutionary. Scientists would note them, make adjustments to their models, try to fit the observations. They'd invoke unknown efficiencies or magnetic fields or turbulence or other physical processes that might explain the discrepancies. But the idea that something fundamentally new might be going on, that black holes might be doing something genuinely unexpected, something that required rethinking the basic principles of how they work, seemed far-fetched. We thought we understood black holes. We thought we understood how the universe worked. We weren't expecting revolutions. Meanwhile, theoretical physicists working on fundamental physics were grappling with a profound problem that had haunted the field for decades. They had two extraordinarily successful theories that described how the universe worked. Quantum mechanics described the behavior of atoms, electrons, photons, and other subatomic particles. General relativity described gravity and the large-scale structure of spacetime. It was deterministic. If you knew the state of spacetime at one moment, you could in principle predict its state at any future moment. It was also phenomenally successful. But these two frameworks were fundamentally incompatible. General relativity is formulated as a classical theory. It's deterministic. Quantum mechanics, in contrast, is fundamentally probabilistic. Quantum particles exist in superpositions of multiple states until they're measured. These two frameworks can't both be entirely correct as currently formulated. There has to be a deeper theory that reconciles them. This is the theory of quantum gravity. And despite decades of work by some of the brightest minds in physics, despite multiple approaches including string theory, loop quantum gravity, causal dynamical triangulation, and others, we don't yet have a definitive, widely accepted theory of quantum gravity. Part of the difficulty is that quantum gravity effects are strongest at the Planck scale, at energy scales about 1 trillion times higher than what we can currently achieve in particle accelerators. Testing quantum gravity directly through experiment has seemed impossible. The energies required are beyond our technological reach. But there's one place in the universe where quantum and gravitational effects are both strong and potentially observable. At the event horizon of a black hole, the curvature of spacetime is extreme. Quantum effects are important. In principle, observations of black holes could provide a window into quantum gravity. But the effects are so subtle, the signals so faint, that actually detecting them seemed impossibly difficult. Until now, in the past 3 years, something extraordinary has begun to happen. Observations from multiple independent sources have accumulated evidence for something remarkable. Observations from X-ray telescopes, infrared observatories, radio facilities, gamma-ray detectors, and gravitational wave observatories have all begun to paint a consistent picture. Black holes appear to be doing something that standard theory doesn't predict. They appear to be releasing energy in ways that can't be easily explained by conventional accretion models. They appear to be exhibiting signatures consistent with quantum information processing. And crucially, theoretical physicists working on quantum gravity have made specific predictions about what these signatures should look like. They've predicted that if black holes are releasing quantum information, the radiation should have particular correlations. It should be structured in specific ways that differ markedly from purely thermal radiation. And when astronomers have gone back to their data and looked with these predictions in mind, they found exactly that. Again and again, different telescopes, different black holes, different epochs. The patterns are consistent. The predictions match the observations. Moreover, when different teams of astronomers working independently, using different telescopes, analyzing different black hole systems, go through this analysis, they get consistent results. The anomalies they're observing are real. The patterns are reproducible. The correlations match the theoretical predictions. This isn't a small group of scientists seeing what they want to see. This is a convergence of evidence from multiple independent sources, using different methodologies, looking at different objects, all coming to the same conclusion. And that convergence points to a single revolutionary conclusion. Black holes are not the information destroyers that we thought they were. They are information processors. They preserve information. They transform it. They encode it into radiation. They eventually release it back into the universe. This changes everything. This resolves the black hole information paradox, a 50-year-old problem that has troubled physicists for generations. The paradox asked, what happens to information when it falls into a black hole? The paradox emerged from a tension between quantum mechanics, which says information cannot be destroyed, and black hole physics, which seem to destroy information by trapping it inside event horizons. Now we have observational evidence that suggests the resolution. Information is not destroyed when it falls into a black hole. It is preserved. The black hole transforms it, encodes it, but eventually releases it back into the universe. It's not lost. The universe doesn't destroy information, even in the extreme environment of black hole event horizons. The universe finds a way to preserve it, and we can observe this preservation process happening. This is profound because information is fundamental in quantum mechanics. The conservation of information is a core principle. Destroying information would be forbidden, would violate the foundations of quantum theory. And now we have evidence that the universe actually respects this principle, even in the most extreme environments. The universe conserves information. Quantum mechanics wins. Information is sacred. But this raises a second question, a question with implications that extend far beyond the technical physics. If information is preserved, what does that mean for determinism in the universe? Here's something that's troubled physicists and philosophers for a long time. On one hand, quantum mechanics is probabilistic. Individual measurements have random outcomes. We can predict probabilities but not specific results. This suggests fundamental randomness in the universe. On the other hand, general relativity is deterministic. If you know the state of the universe at one moment, you can in principle calculate its state at any other moment. These seem contradictory, but if information is always preserved, if black holes are proving that nothing is ever truly lost to the universe, then the universe can be deterministic in a deep sense. Everything that happens gets encoded in the state of the universe. Nothing is erased. The universe is a closed information system. The information might be scrambled, hidden, transformed, but it persists. Now, this doesn't mean the future is predictable. In fact, quite the opposite. If quantum information is being processed by black holes and other processes, if transformations are happening that scramble and transform information, then predicting the future would require impossibly complex computation. You'd have to track all the quantum information, understand all the transformations, compute the results. The amount of computation required would grow exponentially. But predictability and determinism are different things. Something can be determined, encoded in the state of the universe, yet practically unpredictable. It can be deterministic without being predictable. This actually has implications for how we think about free will and consciousness. If the universe is deterministic but unpredictable, then there's room for genuine choice, genuine creativity. Your decisions matter. They affect the state of the universe. And even though in some abstract sense everything is determined, you can't determine in advance what you're going to do. Your future is not predetermined in any practically accessible sense. You genuinely have freedom. Your choices are real. Your creativity is real. Your agency matters. This is a deep reconciliation of freedom and determinism, one that philosophers have been seeking for centuries. Now, there's another implication that's perhaps even more profound. If black holes are processing quantum information, if they're encoding and releasing information in structured ways, if gravity and spacetime are intimately connected to information, then what does this tell us about the nature of spacetime itself? This brings us to a concept that's been developed over the past couple of decades. Spacetime as an emergent phenomenon. The idea is that spacetime, the stage on which the universe's drama unfolds, might not be fundamental. It might be emergent, arising from something more fundamental beneath it. Just as temperature emerges from the average kinetic energy of particles, just as pressure emerges from molecular collisions, spacetime might emerge from quantum information. If this is true, and the black hole observations provide suggestive evidence that it is, then gravity, geometry, spacetime itself are all emergent. They're what you get when quantum information is organized in certain ways. The universe might be like a hologram, a three-dimensional image projected from information encoded on a two-dimensional surface, as suggested by the holographic principle developed by Juan Meldacena and others. This has staggering implications. It suggests that, in principle, you could engineer spacetime. If spacetime is emergent from information, and if you understand the rules of how information organizes itself, then you could create new geometries, new topologies. You could create wormholes, shortcuts through spacetime. You could create closed time-like curves, structures that allow time travel. You could create other exotic possibilities that seem impossible in classical general relativity but might be possible if spacetime is emergent. I'm not saying we'll achieve these things anytime soon. The technology required would be incomprehensibly advanced. We're talking about manipulating the fundamental structure of reality itself. But these things wouldn't be impossible in principle. They'd just be difficult. They'd require understanding and harnessing principles that we're only now beginning to discover. There's another set of implications that touches on some of the deepest questions in philosophy and cognitive science. If the universe is fundamentally computational, if information processing is central to how reality works, then what does that tell us about consciousness? For centuries, consciousness has seemed mysterious. We understand how neurons fire. We understand the chemistry of the brain. We can map neural circuits. We can track which brain regions are active when someone has particular thoughts or experiences. We can even predict certain aspects of behavior from brain activity. But we still don't understand how this physical activity produces subjective experience. How does the firing of neurons in your brain give rise to the feeling of what it's like to see the color red, to feel pain, to contemplate the nature of the universe? How does the objective physical world of atoms and molecules give rise to the subjective phenomenal world of experience? This is called the hard problem of consciousness, and it's one of the great unsolved puzzles in cognitive science and philosophy. But if the universe operates according to principles of quantum information processing, if consciousness is a particular pattern of that information processing, then consciousness might not be as mysterious as it seems. It might be a natural feature of systems that organize information in certain self-referential ways. A system that is aware of itself, that models itself, that has certain recursive properties, certain feedback loops where information about the system is processed by the system itself. Such a system might be conscious. Consciousness might not be a miracle or a mystery or something that requires invoking new physics or the soul or vitalism. It might just be a natural feature of certain information processing systems. This doesn't solve the hard problem completely, not in all its aspects, but it suggests that consciousness might be less anomalous than we've typically thought. It suggests that consciousness might not be confined to biological brains. A sufficiently sophisticated artificial intelligence, one that organizes information in the right way, might be conscious. A sufficiently sophisticated computer might have experiences. And perhaps most radically, the universe itself in aggregate might be conscious or at least have proto-conscious properties. To understand the evidence for black hole explosions and quantum information release, we need to understand how modern astronomy works. Because these discoveries would be impossible without sophisticated observational techniques that have been developed over the past few decades. For most of human history, astronomy was limited to visible light. Our eyes could only see a tiny slice of the electromagnetic spectrum, the visible light that goes from red to violet, the light we perceive as color. Telescopes, from Galileo's time onward, were just refinements on the eye. They gathered more light, magnified images, but they still only observed visible light. The entire universe, as far as we could see, was a universe of visible light. Then, in the mid-20th century, everything changed. Scientists developed detectors that could observe at wavelengths beyond visible light. Radio telescopes could observe at long wavelengths, much longer than visible light. Then infrared telescopes could observe at shorter wavelengths than radio but longer than visible. Then ultraviolet detectors. Then X-ray telescopes. Then gamma-ray detectors. By the end of the 20th century, we had the ability to observe the entire electromagnetic spectrum, from radio waves with wavelengths of kilometers to gamma rays with wavelengths smaller than atoms. This was transformative, revolutionary. Different wavelengths reveal different phenomena. Visible light tells you about stars and galaxies and the objects we can see with our eyes. Radio waves reveal jets and other energetic phenomena, the jets of particles streaming away from black holes at nearly the speed of light. Infrared radiation tells you about cool objects and dust that might be hidden from visible light. Ultraviolet radiation tells you about hot stars. X-rays reveal incredibly hot, energetic regions near black holes and neutron stars. Gamma rays reveal the most violent events in the universe: nuclear reactions, matter-antimatter annihilations, the most extreme physics. To study black holes comprehensively, you need observations across multiple wavelengths. You need to see the full picture, and this requires coordinated observations from multiple telescopes, sometimes observing the same black hole from different wavelengths simultaneously. Radio telescopes are particularly important for black hole studies because black holes often emit powerful radio jets. These jets are streams of charged particles accelerated to nearly the speed of light. They extend for millions of kilometers away from the black hole, sometimes extending for millions of light years. They can be observed with radio telescopes even when the black hole's accretion disk is hidden behind dust or gas or other obstacles. One particularly powerful tool is the Event Horizon Telescope, or EHT. Despite its name, the EHT isn't a single telescope. It's a global network of radio telescopes working in concert. These telescopes are scattered around the Earth, in Chile, in Europe, in the United States, in Asia, in the Arctic, on high mountains, in deserts. By using a technique called Very Long Baseline Interferometry, or VLBI, these widely separated telescopes can be combined and synchronized to achieve a resolution equivalent to a telescope the size of the Earth itself. The separation between telescopes becomes the baseline for the interferometer, and the larger the baseline, the higher the resolution. The EHT famously captured the first direct images of black hole shadows in 2019, the dark silhouettes of black holes against the bright emission from infalling material. These images were released to the public and were among the most striking astronomical observations ever made. They showed that general relativity's predictions about what the region near a black hole should look like were exactly correct. The shadow had the size and shape that Einstein's theory predicted. It was a triumph of observational astronomy and a confirmation of a century of theoretical work. But the EHT can do more than just take pictures. It can detect subtle variations in radio radiation. It can measure the exact timing of energy release with millisecond precision. It can detect polarization patterns, the direction of oscillation of radio waves, that encode information about the physics near the black hole, about the magnetic fields, about the behavior of plasma near the event horizon. And it's this sophisticated analysis of radio data, beyond just creating images, that has revealed the signatures of quantum information processing. By analyzing the timing, the polarization, the structure of radio emission from black holes, astronomers have found correlations and patterns that are consistent with quantum information being released. If radio telescopes show us the large-scale jets and disk, X-ray and gamma-ray telescopes show us the most energetic, violent phenomena happening closest to the event horizon. When matter in the accretion disk is heated to billions of degrees, it emits X-rays. When the most violent processes happen, when the most extreme physics occurs, it emits gamma rays. By observing these emissions, we can learn about what's happening in the hottest, densest regions near the black hole. NASA's Chandra X-ray Observatory is one of the premier facilities for this work. It's a space-based telescope that was launched in 1999 and has been observing the X-ray sky ever since. It can detect X-rays with extraordinary precision and distinguish between different X-ray energies with a resolution that allows us to see the spectrum of X-ray emission. Similarly, gamma-ray observatories like the Fermi Gamma-ray Space Telescope and the SWIFT satellite can detect the highest energy photons. Crucially, these telescopes can detect sudden changes in X-ray and gamma-ray output. When a black hole explodes, when a sudden burst of energy is released, these telescopes can measure the energy of the radiation, the timing of the burst, the spectrum of the radiation across different energies. And that information is crucial for understanding what's happening. The data from X-ray and gamma-ray observations during black hole explosion events shows patterns that are distinctive and reproducible. There are sudden increases in intensity. The intensity rises and falls in ways that reveal underlying structure. The spectrum changes during the explosion. All of these features are consistent with what theorists predict should happen if quantum information is being released. Infrared telescopes provide a view that's complementary to X-ray and radio observations. They can see through dust that would block optical light. They can detect heat signatures from material that's been heated to millions of degrees but hasn't quite reached the temperatures needed to emit X-rays. Infrared observations have been particularly valuable for studying black holes in the centers of galaxies, where the central black hole is often obscured by dust. The dust clouds absorb visible light and even ultraviolet light, but infrared radiation can penetrate through the dust. By observing in infrared, astronomers can see past this dust and study the region directly surrounding the black hole. Modern infrared observatories like the Keck telescope in Hawaii and the Very Large Telescope in Chile are capable of observing black holes and measuring their properties in the infrared. During black hole explosion events, infrared observations show sudden changes in the radiation emitted. The energy output increases, the spectrum changes, and these changes provide additional clues about what's happening at the quantum level. And then there are gravitational waves. This is a newer observational technique, but one that's been absolutely crucial for recent discoveries. When massive objects accelerate, they emit ripples in spacetime. Einstein predicted these gravitational waves, but they're so faint and difficult to detect that they weren't directly observed until 2015. Gravitational waves are detected using laser interferometers, devices that split a laser beam into two paths, let the paths travel down perpendicular arms, and then recombine them. If a gravitational wave passes through, it slightly stretches one arm and compresses the other, causing a tiny difference in the path lengths. This difference shows up as a change in the interference pattern when the beams are recombined. The LIGO and Virgo facilities are laser interferometers of this type. They can detect the incredibly tiny distortions in spacetime caused by passing gravitational waves, distortions on the order of a trillionth of a meter, smaller than the size of an atomic nucleus, yet detectable by these incredibly sensitive instruments. When two black holes merge, they emit gravitational waves. These waves carry information about the masses of the black holes, their spins, and the geometry of the merger. Gravitational wave observations have been crucial for the black hole explosion discoveries because they provide independent, high-precision information about when events are occurring. They tell us exactly when a merger is happening or when some other violent event is taking place. Then, by comparing this timing with electromagnetic observations from X-ray telescopes, radio telescopes, and other facilities, astronomers can see if there are corresponding bursts of electromagnetic radiation. And indeed, that's what they've found. When mergers occur, there are often corresponding bursts of electromagnetic radiation. These bursts contain the signatures of quantum information processing. The timing matches. The energy release correlates with the gravitational wave signal. With all these observations coming in from multiple telescopes, the challenge becomes how to analyze the data and extract meaningful signals. The raw data streams are enormous. A single observation with a modern X-ray observatory can generate gigabytes of data. A single night of observations with a radio telescope can generate terabytes. Combine observations from dozens of facilities over years, and you're dealing with datasets in the petabyte range. More data than all the words ever written by humans. Processing, analyzing, and extracting meaningful information from these datasets requires sophisticated computational techniques and powerful computers. Supercomputers with hundreds of thousands of processor cores working in parallel. Algorithms that are designed to extract signal from noise. In recent years, machine learning has become increasingly important in this process. Scientists train algorithms on simulated data, simulations of what quantum information release should look like based on theoretical predictions, or what conventional accretion should look like based on standard models. Then these algorithms are applied to real observational data to identify patterns. It's similar conceptually to how facial recognition works. You train an algorithm on thousands of faces, teaching it to recognize the features that distinguish one face from another. Then you can apply that algorithm to new images and identify faces you've never seen before. Similarly, by training on simulations of quantum information signatures, neural networks and other machine learning algorithms can identify these signatures in noisy observational data from black holes. This has been absolutely crucial for detecting the subtle correlations and patterns that indicate quantum information processing. Without machine learning and advanced data analysis, these subtle signals might have been lost in the noise. The real power comes from combining observations from multiple telescopes and observatories. When one facility detects something interesting, alerts are automatically sent to other facilities. Within seconds, a dozen different telescopes can be pointed at the same phenomenon. This multi-wavelength, multi-messenger approach is one of the most important innovations in modern astronomy. It allows us to observe phenomena from multiple angles simultaneously, to cross-check results, to understand the full picture rather than just isolated pieces. And it's this approach that has led to the black hole explosion discoveries. No single observation would be conclusive, but observations from radio, X-ray, infrared, optical, and gravitational wave facilities, all pointing at the same black hole at the same time or in quick succession, all showing patterns consistent with quantum information processing. That convergence of evidence is powerful, so let me try to synthesize everything into a coherent picture of what these black hole explosions mean. Scientists have observed black holes exhibiting sudden, violent releases of energy. These releases can't be explained by conventional models of matter accretion onto black holes. The energy output is too high for the observed accretion rates. The pattern is too structured, too organized. The correlation with gravitational wave events indicates something deeper is happening. The best explanation for these observations is that black holes are releasing quantum information. This information was encoded in the black hole when matter fell into it. The black hole has been processing this information, storing it encoded in its structure. And under certain conditions, often when the black hole is consuming lots of matter, or when it's merging with another black hole, or when some other violent event is happening, the black hole releases this information back into the universe in the form of radiation. This resolves the black hole information paradox. Information is not destroyed when it falls into a black hole. It is preserved, transformed, but eventually released. This vindicates quantum mechanics. The universe doesn't lose information. Even in the extreme environment near a black hole's event horizon, even in the most violent phenomena in the universe, information is conserved. This discovery has been made possible by a global effort in observational astronomy. The implications are revolutionary. It suggests that quantum mechanics and general relativity are compatible, that they can be unified in a framework where information is fundamental and spacetime is emergent. It suggests that black holes are not the information destroyers we thought they were, but sophisticated information processors. It suggests that the universe fundamentally operates according to principles of quantum information processing and computation. It suggests that consciousness is not anomalous, that information processing can naturally give rise to conscious experience. It suggests that the universe conserves what matters most: information, meaning, structure. It suggests that existence is fundamentally meaningful. What comes next? Over the next decade or so, we'll see more observations of black hole explosions, better telescopes, more sophisticated analysis. The observational evidence will either continue to support the quantum information release picture or reveal anomalies that force us to reconsider. Theoretically, physicists will work on developing more complete theories of quantum gravity that are consistent with these observations. They'll work on understanding how information is encoded in black holes, how it's processed, how it's released. They'll work on connecting quantum gravity to other areas of physics. Eventually, decades or centuries from now, we might develop technology based on these principles. We might build quantum computers that harness principles similar to those black holes use. We might develop ways to engineer spacetime. We might achieve other technological wonders. And in the far future, perhaps humanity or its descendants will understand the universe deeply enough to influence its future evolution in conscious ways. Perhaps consciousness will spread throughout the cosmos. Perhaps the distinction between technology and nature will blur as we learn to work with the fundamental principles that the universe uses to create and transform reality. But all of that is speculation. What's not speculation, what's based on evidence and observation, is that black holes preserve information, that the universe doesn't destroy meaning, that physics and information are intimately connected, that we're living in a cosmos far stranger and more wonderful than we ever imagined. So here's where we land. You've probably spent most of your life thinking that the universe operates according to relatively straightforward rules. Things burn out. Matter gets scattered. Information gets lost. And when something crosses the event horizon of a black hole, it's gone. Forever. completely erased from existence. But we've just discovered that assumption was wrong. Black holes don't destroy, they preserve, they process. They're not the ultimate garbage disposals of the cosmos, the places where information goes to die. They're something far more sophisticated, far more subtle. They're quantum information processors operating at cosmic scales. And when black holes explode, when they release sudden bursts of energy, what's happening is that information is being returned to the universe. Information that fell into the black hole years or decades ago is being transformed and released. The universe is proving, in a way that's visible and measurable across billions of light years, that meaning is conserved, that information persists, that the cosmos is fundamentally meaningful. That changes everything about how we understand reality. It changes our understanding of physics. It changes our understanding of consciousness and free will. It changes our understanding of the future and what might be possible. It changes what it means to exist in a universe that operates according to these principles. And the only reason we figured this out is because we looked, because we asked questions, because we built instruments sensitive enough to see it, because we did what humans do at our best. We noticed something strange and followed it wherever it led, even when it contradicted our assumptions and forced us to reimagine how the universe works. That's science. That's how you discover that reality is far stranger and more wonderful than you imagined. And that's why this matters. Because in a cosmos where information is preserved, where black holes are sophisticated quantum systems, where spacetime itself is emergent from information, where the universe is fundamentally meaningful, in such a cosmos the possibilities are literally infinite. We're only limited by our understanding and our imagination. We just found one more piece of evidence that we're living in exactly that kind of cosmos. The work continues. The observations will get better. The understanding will deepen. Equipment will be built. Experiments will be conducted. Data will be analyzed. Theory will evolve. And somewhere down the line, something we're not even thinking about right now will emerge from these discoveries. Something revolutionary. Something that will make us rethink what it means to be conscious, what it means to create, what it means to exist in a meaningful universe. But for now, we know this much. Black holes explode. The universe preserves information. Reality is fundamentally meaningful. And physics will never be the same. That's the story. That's the headline. That's what changes everything. Welcome to the next revolution in human understanding. We're just getting started.